The title is A New Perspective of the Subduction Zone Derived from the Ocean Drilling Program for the Nankai Trough Seismogenic Zone Experiment, NANTRO-SEIS. The speaker is Gak Kimura. Please start.
Okay, thank you, Kinoshita-san. And today I'd like to talk about the NANTRO-SEIS from the beginning, because what kind of the perspective we are now from that project. Because the initial science plan long time ago, 2001, so the seismogenic zone initiative they set up like this. So the non-riser drilling and the riser drilling together with the borehole observatory and ocean floor network. And so we understand that we quantified lateral changes in the nature of the physical, chemical, and hydrological change in the subduction fault. And so before going this operation, we did the 3D seismic survey here. So at this moment, the 2007 drilling started. But after that, 2011, Tohoku earthquake took place. This is so serious, as you know. So the seismogenic zone challenges, and the first we set up like this. What governs the subduction zone seismogenic fault, the locking versus stable slip and transitional fault behavior? Does the fault state evolve during the interseismic and pre-seismic period? If so, how? So what governs tsunami generation characteristic for a given great earthquake? So we expect NANTRO-SEIS concept to address these questions. And so we did, and we started the operation and the Nankai Trough off Key Peninsula. The reason why here is that the 1944 and 1946, all the Nankai to Nankai earthquake started from this place. And so 2007 we started, already 10 years. And so we so far, and the 10 years and the last year, and already the 11 expedition here, so more than 200 scientists from 15 countries involved in this project. So the 13 main site, so the maximum depth so far, 3,058 the meters below sea floor. So the most extensive logging while drilling program and downhole stress pressure. Most advanced seafloor borehole monitoring system achieved, now streaming data in real time to land. And so far, more than 100 papers published and still going. And so, the first, what is the main outcome of science? This is important. So we, first year and second year, we drilled a very frontal portion of the splay fault and plate boundary decoma. We dated, and so by using the nanofossil and the microfossils. And so all of these sediments are quite young. So on the basis of that dating, we can say that the splay fault itself the activity is quite young, and so the accretion prism, especially on the outer part of the accretion prism, quite huge, but all of them are grown since 2 MA. So this is very interesting. And also, the addition to that, we drill into the Kumano Fork Basin and into the accretion prism. Again, all of these are quite young, especially after the 2 MA, most of the Kumano Basin and the Fork Basin filling. And even the Venistad and the slope basin, and it's the much deeper setting, and just only after the 6 MA. It's the latest Miocene to the Pliocene and Pleistocene. And so the geological point of view, this is quite young. And so we drill into now the 3 kilometers below sea floor even that the depth, the age is just only 7 million. It means that entire fork now here is quite young and so very rapid growth. And maybe that is very related to the how wide and here the large earthquake set up for the hanging wall. So this is very important background. So the Nanto project, we recovered shallow portion of fault and from the frontal thrust and up the end of the mega spread fault system. So the fault itself is quite amazing. And so this is the spread fault out of sequence fault site, and this is the frontal part of Dekoma. You can see that this just a little bit darker portion here and here, just only several millimeters thick, and this part is slip, the fault gouge, surrounded by the still unliquefied the silty sediment, and so this is the slip surface, and so quite thin, and so we analyze this first. The vitrinite reflectance. This is very good signal for summer signal, and show us that this slip part is heated up. And the vitrinite reflectance converted to temperature show us that is more than 300, and so in this case almost 400 degrees C. And so this is the friction heating. And so we published here this paper, Sakaguchi et al., and so the combined paper and clay mineralogy, and very interested the secret history. Now this paper is so. The review process, so many criticism. But during the paper review, Tohoku earthquake took place. Immediately this paper accepted. Because in the case of Tohoku earthquake, slip propagated to trench. So it means that the very shallow portion, very high velocity slip is possible. So this is very important. So this result changed the Japanese Central Disaster, committee or something, quite top of the cabinet, changed maximum size of Nankai on the basis of this result. And so this is very important and the scientific result. And so many people analyzed friction property from that gouge, from very slow velocity to quite high earthquake, like high velocity friction experiment. All of these friction experiments show us, in the case of slow, the velocity and the friction coefficient is like this. But if the velocity beyond 10 to minus 2 meter per sec, and this is relatively high, and so this scale of earthquake seismic and the velocity scale, everything they weaken. This means that all the material, all the gauge material, if the velocity beyond this scale, rupture quite easily propagate to the trench. This is a very important scientific result. And so many holes we drilled so far, and so like this breakout show us the stress and the condition, stress state here. So most of these sites now the vertical the stress, so now gravity dominated stress field. But the interesting scientific result is that the horizontal maximum stress orientation. Most of these in parallel with the plate convergent direction, and except for this part, this is interesting, but I skipped the discussion here. So the stress field revealed by using this breakout result and the leak-off test and the inelastic rebound and analysis of the recovered core. So all of these show this kind of stress field. So this is the stress field condition here, hydrostatic and the lithostatic. And so the several methods show us stress fields now very close to the overburden lithostatic level. If this stress field beyond the vertical level, it means that the stress field changed to normal fault type to strike slip or the reverse fault field. And it means that if this stress field reach horizontal maximum beyond the friction strength of the fault, it means that start to break. So where we now is quite important. How dangerous Nankai Trough at this moment. So that kind of the result is the main result of so far the Nankai Trough. But if we combined with other investigation, it's quite interesting. This is the very recently the paper and the acoustic GPS of the ocean floor geodetic measurement show us this kind of the red arrow. So the combined with the on-land result, the vector show us. And the hanging wall side is coupled with subducting Philippines plate. And they estimated this slip deficiency, it means that the difference between the real observation and plate convergence suggests that some part is strong coupling, other part is not so strong coupling. And so such a result is now going. So this is very new observation. Combined with that, and we can know the much more detail the present status of this region. So drill hole, so far, next talk, Damian presented that the result of Warhol Observatory. And so that result is very interesting. Because this is maybe Damian presented next. Last year, April 1st, Nankai Trough plate boundary and the earthquake took place. Okay, so after that, slowly propagated to the very shallow portion. Here we plan to drill and the borehole this year. And so almost this is the last. The Nankai Sea project. First initial science plan almost completed, except for the very deep riser hole. And here, the reaching to the plate boundary fault, it's a root of megasplay fault and revealed the scientific target. And so here we did that. 10 years ago, this is 3D seismic survey result. We reproduced, processed. It is very clear, much more. And so also, this is plate bound spray fault here. And so the velocity model is so different from the previous one. And so we are now here. The target is here. And so this part is quite high velocity beyond that 5 kilometers per sec. And this is quite hard rock. And so this part is possible to store the elastic energy. And so this is the last one. And this year, again, we will visit to the frontal part, borehole, observatory installation, and after that, final target, deep riser and approaching to the plate boundary. If possible, we want to pass through that. And so how much urgent status is the seismogenic zone? We want to know. And so the answer, we hope, comes soon. And so the key observation is like this. Thank you.
Thank you, Gaki-san. Okay, next speaker is Damian Seifer. The title is Repeating and Triggered Slow Slip Event in the Near Trench Region of the Nankai Trough Detected by Borehole Observatories.
Okay, so thanks. I want to thank the conveners for inviting me to share some pretty exciting recent results. This is work that has come out of IODP Expedition 365, which was completed just about a year ago. I'm going to jump right in, but first just note, so these are the only photographs of the observatory instruments that you're going to see. The rest of this will be schematics and then data. But so this is one of the permanent observatory wellheads showing the valving and the pressure sensing unit. And this goes at the top of the wellhead, and then, or at the wellhead, and then all the all the sensing is down the borehole. So this is on the ship as it's about to be lowered. This is sort of one type of instrument from which I'll show you data. And then the other is a temporary set of instruments that we had installed in another borehole for 5.5 years, recording data, and that was retrieved during this expedition as well. And of course, this is work that was funded, jointly implemented by IODP, and funded, the instruments and the drilling funded through JAMSEC and NSF. Okay, so I think Gaku did a great introduction to the region. So this is part of the NantraSeis project. And so here's a seismic cross-section showing the locations of many of the boreholes. Most of these the smaller ones here, the black boreholes were holes that were drilled in cord or LWD, logging well drilling data, were collected with geophysical logging. The holes I'm going to talk about are the colored ones here, sites C2 and C10. And throughout this talk, C2 will always be blue, and C10 will always be red. These are two sites where we have borehole observatories monitoring at depth of roughly 1 kilometer at site C2 and roughly 400 meters at site C10. And so the data I'll show you come from these circles right here in the subsurface. In map view, why this is an interesting location is that it's really right on the fringes of the high slip zone from the 1944 Tonankai earthquake. So what's shown here are slip contours of 0.5 meters. And so we're kind of straddling the upper edge of high slip, co-seismic slip in that large earthquake. Gaku mentioned the April 1st earthquake in 2016. That epicenter is shown here. And then the maroon shows the seafloor network, the DUNET seafloor network nodes. So each of these points is a data, an instrument cluster that includes absolute pressure gauges at the seafloor, and so that'll come into the talk in a minute, and also seismometers that we use to locate some of the low-frequency earthquakes and microseismicity that Gaku showed a quick map of that in the last talk, and I'll show you some of that here. So we have, I guess the point here, one key point is that we have really good coverage to locate any microseismicity or low-frequency tremor or earthquakes through the cabled network, and then we have the boreholes to get into the subsurface. Okay. So this borehole was a permanent installation that was put in 2012, put in 2010 as a permanent observatory, and then real-time data transmission through the cabled network began in early 2013. So here I'll be showing you data that mostly come from that permanent observatory installation that's more complete and cemented into the borehole. Here I'm going to show you data from a temporary set of instruments that were suspended in the borehole and in hydraulic communication with the fault zone here, the splay fault here. Okay, so first, again, this permanent installation, what does it look like at site C2? So zooming in on the seismic, the borehole went through this Kumano Basin sediments and into the upper part of the accretionary prism. We're actually monitoring, it's a multi-level and fairly complex observatory. It includes pore pressure sensing at 750 to 770 meters in the Kumano Basin. Additional pore pressure sensing just short of 1 kilometer, 950 meters roughly, at the bottom of the hole. So two locations of pore pressure sensing. And then in between those, we've cemented in strain and tilt meters right in this zone here, kind of the very lowest part of the Kumano Basin where it's a uniform mudstone. I'm going to focus today on the pore pressure records at the bottom of the hole, which provide the best proxy for volumetric strain. And this is because it's most distant from the seafloor and it's a relatively low permeability part of the formation. So moving on to site C10, again, just to give you a sense for what the borehole configuration looks like. Here, again, zooming in on the seismic, we have a borehole that was drilled to a total depth of about 550 meters below seabed. And we've got casing in that borehole that protects the borehole, and it's perforated or screened right at this fault zone, the splay fault that branches up off of the master detachment at depth. And we are monitoring pore pressure in a sealed interval. It's sealed off by a plug. So we're basically measuring formation pore pressure in this zone here at about roughly 400 meters below seabed for the monitoring interval. And these instruments were pulled out as standalone instruments, pulled out, and the data were downloaded roughly 1 year ago, and they preserved a 5+ year record of pore pressure in the formation. So the key thing here, and what I'll talk about for the rest of the talk, is those pore pressure records at those two locations provide a very sensitive measure of the volumetric strain in the formation, and you can actually calibrate this or calculate the relationship between pore pressure and strain if you know something else about the rocks, like the compressibility and the porosity. We know this from laboratory measurements on core samples from previous drilling at these sites. And so we actually have a measure that essentially roughly 5 kilopascals of pressure change corresponds to about 1 microstrain. And so that's how we actually quantify the strain directly from the pore pressure. And one really nice thing about this is that, as Gaku mentioned, we had this earthquake in April of 2016 that's very well characterized because it was monitored in the near field. So we know a lot about the source and the slip distribution in that earthquake. We can actually use an elastic model to make a prediction of the strain that you would predict from that earthquake at our borehole observatories. And it's a very nice kind of field calibration and gives us basically the same answer that we get from an independent calculation or prediction of that conversion. So we have a lot of confidence that we're able to rigorously use pore pressure as a proxy for strain quantitatively. Okay, so enough about the background. Here are the data. So I want to show you, really kind of highlight some of the things we're seeing, and it's pretty cool, I think. So basically what we're seeing is that a series of pore pressure transients that occur over periods of a few days to several weeks in the boreholes. And so what's shown here are records where we've removed the tidal signal to the best that we can. So there's still residual. This residual tidal signal is really just about 1 to 2% of the tidal amplitude. So we've removed the tides, and what we see are synchronous changes in pressure, which we interpret as strain events at the 2 boreholes. And in some cases, we see mixed modes where site C2 goes into dilation and site C10 goes into compression. In other cases, we see more complicated events. So we have kind of a whole family of these events. Again, the onset is synchronous at the 2 sites, so that suggests it's some kind of regional strain or slip event, and a variety of kind of flavors of polarity and sign. So some of these appear to be triggered. So here's an example of a slow strain transient following the Tohoku earthquake in 2011. Here's an example of one in August of 2016 that basically arose spontaneously. Did not follow any known earthquake, right? And this one is a mixed mode. This one is extensional at both sites. So we see, again, a variety of styles of events. To first order, one of the things that we can do is we can use the polarity or the sign of the strain, whether it's dilation or compression, to make a kind of a preliminary interpretation about where slip must have been occurring if it were located on the plate interface. And so, for example, I'm showing you now, if we just focus on the first part of this relatively complicated event, it's dilating at site C2 here. So this is an extension. And this site, we're seeing compression. So you can do that relatively simply by having slip down here over a zone on the plate boundary that is centered beneath the sites and between them. And that would be compression here and extension here. The reason I chose this as an example is that this particular event is one of the more complicated ones, because you see what happens at site C10 is the sign changes about halfway through the event. And so the interpretation here, again, just kind of to give you a flavor for how you can use these data to say something about where slip might be occurring, is that the way to get dilation at both sites would be to move the slip further up dip. So the interpretation of this particular event, and I'll show you further evidence for this in about 2 slides, is actually that this represents a migrating slow slip event along the plate interface that was initially between the 2 sites and below them, and then moved farther to trenchward. Okay. So one of the other observations that's a really important corroboration of the interpretation of slow slip on the plate interface is that we observe using the DUNET network, and now this is zoomed in, so the triangles show the seismometer locations. These are low-frequency tremor, so this is filtered at the 2 to 8 hertz range. And a couple of key observations here. One is that there is concurrent low-frequency tremor with many, but not all, of these strain transients. It appears to be on the plate interface and, for the most part, in these regions here, from C2 toward the trench. But it doesn't seem to map perfectly to the location that we expect the slip based on the strain events, and it doesn't match in time. And so that's shown here. This gray bar is the time of those low-frequency tremors, but it's pretty clearly well after the onset of strain. So in this case, we see low-frequency tremor and slip that's concurrent with part of the slow slip event, but part of the slow slip event appeared to be sort of silent, didn't radiate energy. We have other cases where the tremor, here's the time series of tremor, it's basically occurring during the entire period of the strain transient. And this is the example that Gaku showed. This is the triggered slow slip and tremor from the April 2016 Kumamoto, the magnitude 6 earthquake off me, and then the Kumamoto earthquake. So those are sort of two different flavors, the triggered kind, the spontaneous kind that give you low frequency tremor. And the third flavor is the kind that's mostly silent. And so here's a spontaneously arising slow slip event, but there's very little tremor to speak of above the background. There are persistent clusters of tremor for all of the events. One little cluster here located near the trench and one along strike roughly 20 kilometers. So if you kind of go back, these are sort of always there in those patches, and suggest that maybe there's some characteristic of the plate interface at these particular spots that makes it able to radiate energy. But for the most part, most of the slip in this event, which would have been centered between the two sites here, isn't related to tremor. Okay. So one of the other things we want to do, of course, is a little bit more quantitative interpretation. And so to do that, again, we have pretty limited data, but we still wanted to try to make an interpretation about trying to understand where slip might occur and how much slip might occur. So for this, we just used a simple elastic dislocation model, really just to roughly evaluate the position and the width of the slipping region. How big is it, where is it, and how much slip needs to occur to give us the signals we observe. And so I just give you the punchline here is that we find that most of these events need to be centered in the neighborhood of 25 to 35 kilometers from the trench, so basically beneath and between the two drill sites. The amount of slip we're estimating is on the order of 1 to 4 centimeters, and this slip occurs in a region of already identified low P wave velocity, high pore fluid pressure, and low effective stress. And so what I want to leave you with in this talk is here. And so this is basically now summarizing all of those observations. And so it's not just that we see a number of these events, but they seem to recur semi-periodically. So this is the magnitude of the events in terms of the strain signal or the change in pressure, and this is a timeline. And so we see recurring slow slip events on the plate interface roughly every 12 to 18 months. If you add up the amount of slip, between 1 and 4 centimeters of slip, it varies a little bit from event to event, that's required to explain the strain signals at each of the boreholes. If you add that up, we're talking about something in the neighborhood of 30 to 50% of the plate motion is actually accommodated out here in the outer part of the forearc between the trench and 30 kilometers landward by slow slip events. The slip rates of the events, just some additional sort of trivia, based on the duration and the amount of slip, is on the order of fractions of a centimeter per day of slip, and that's roughly consistent with slip rates at other slow slip event locations that are well characterized, like the Hikurangi events that Laura talked about, and also in Tohoku and Costa Rica, there are a limited number of examples. And then finally, the triggered events seem to be slightly larger, and for the most part, those are the ones that are really out near the trench, whereas the spontaneously arising ones are a little bit farther from the trench, but still quite shallow. So I'll leave it there because I'm running out of time, but also this is my last slide.
Thank you, Demian. The speaker is Magli, and the title is Initial Finding of Power Cruise Research on IODP Expedition 352 Hard Rock Core 1 Pedology and Geochronology.
Okay, well, thank you for inviting me to this meeting. This is going to be something completely different. I'm going to talk about igneous rocks here. So I'm going to talk about the initial findings of the post-cruise research for IODP Expedition 352. Before I get into that research, though, I thought I'd go through some background about why we drilled there. Main reason is because, it likely represents lithosphere that was generated during subduction initiation. And that was based on lots of research that's been done basically since the late 1900s, actually, in the Izu-Bonin Mariana forearc, including DSDP leg 60 that drilled in this area. And there's been a lot of dredging along the trench slope here, and as well as diving. And what it discovered is that this is a naked forearc. It doesn't have an accretionary prism. It basically exposes the basement lithosphere there. So the hard rock basement that's related to subduction initiation is there. And the reason it was considered to be subduction initiation material is because of these really strange rocks that were discovered on Chichijima back in the late 1800s. They're called bonanites because this is the Bonin Islands, and that's the type of locality. And these are high magnesium andesites with very low titanium concentrations. So back in the 70s, there was a lot of experimental work done in these lavas, and there's been some experimental work done since then that shows that they have to be hydrous melts of depleted mantle at shallow levels. And using that idea, basically, several people, starting back, I think, with Aaron Meyer in 1980, thought that these might be related to subduction initiation. And the idea was actually developed most fully by Stern and Bloomer in 1992. So this is a figure from their paper. And what they postulated was that there was an old cold Pacific plate up against a very young hot Philippine sea plate that was basically produced by seafloor spreading shortly before the subduction initiation event. And their idea was basically the Pacific plate, because it was so cold and old, it just started spontaneously sinking. And that sinking caused mantle to upwell into the forearc. And by adding water to that upwelling hot mantle, you produce the bonanites. So starting in 2004, a group of Japanese scientists and American scientists got together and used the Shinkai 6500 to do a lot of diving up near the Bonin Islands and also down south near Guam and the Marianas Islands. And the main idea was to look at this forearc sequence to see what the lithosphere-related subduction initiation looked like. So this is what we found. So the dives are shown here in these little black lines in this one. They're not actually shown in this one. But south of Guam here, the main discovery of our diving was that there was a very thick layer of basalts underneath the bonanites. The bonanites are in blue here, and the basalts are in here. We called these forearc basalts because they were in the forearc. They looked like mid-ocean ridge basalts, but they weren't produced at mid-ocean ridges, and they weren't produced at back arcs. They were probably produced actually sort of in situ. And these were underneath bonanites, and then beneath them were gabbroic rocks and then periddotites. The exact same sequence was found up near the Bonin Islands, and the forearc near the Bonin Islands as well, as with basalt underneath bonanites. And actually, the same sequence is actually found back in 1999 by Dabari et al. They didn't recognize these forearc basalts as what we think they are, which is the subduction initiation-related basalts, but that they were trapped like mid-ocean ridge basalts. So anyway, this sequence basically spans all the way from Japan all the way down south to Guam. This is the sequence that we thought we had at the time, and it's still pretty much true. So there's depleted periddotites basically at the deepest parts of the forearc slope, trench slope. Those are overlain by gabbroic rocks. Then there's our forearc basalts, and these are related to each other, and they erupted at about 51 to 52 million years ago. Those are overlain by bonanites, various kinds of bonanites, basically starting about 49 million years ago up through about 43 million years ago. And about the same time as these transitional bonanites occurred, the actual normal arc rock started erupting. And this sequence seems to have been true all the way from, again, Japan all the way down to the area south of Guam. Now, those of you who are familiar with ophiolites, which are basically slivers of oceanic crust on continents, you could see that this is the exact same sequence you find in ophiolites. And so because of this, and this supported ideas that have been out there ever since this paper by Cameron in 1979, that perhaps ophiolites are not pieces of like mid-ocean ridge basalt crust. Instead, that they could be basically related to subduction initiation. They're basically forearc sequences. So that was the work we did by diving. Now we moved on to drilling. Basically, we wanted to look at the volcanic sequence in great detail to see basically what happens in mantle sources, how the mantle sources change through time, and how melting processes change through time right after subductionation and on through bonanite production. And this is a picture that was just taken actually on the ongoing expedition, which is probably the nicest picture I've seen of the JOIDES resolution. So our expedition took place here in the Bonin Forearc, basically to the northeast of Chichijima. We sighted it based on Shinkai 6500 diving nearby that showed that the stratigraphy of the forearc looked something like this. There was periddotites at depths. They were overlain by gabbros, and then basically doleritic rocks were here. These are basically sheeted dike complexes. And then those are overlain by forearc basalts and then bonanites. So we sighted our deepest hole site U1440 to drill from phoric basalts into dolerites. And we basically, and then sited the shallower one, 1439, to drill from bonanites down into the phoric basalts. And hopefully by doing that, we'd get the entire volcanic sequence related to subduction initiation. Well, we couldn't get as deep as we wanted in both holes because of drilling issues, and we also saved a lot of time when we drilled by drilling in the casing. So we ended up with basically time to drill 2 more holes, and those were sites 1442 and site 1441. And we pretty much accomplished our goals. This is the stratigraphy that we found in these 4 drilling sites. This is site U1440 here. We basically had phoric basalts, and we drilled down into underlying dikes. Site 1441, we didn't get very deep because of drilling issues. Site 1439, basically a wide variety of bonanites ending into what we think is another dike complex down here. And then 1442 was basically just another sequence of very complex bonanites. So I'll go through these in sequence. The lavas we found at site 1440 were basically apheric lavas that had compositions that are very much like mid-ocean ridge basalts, except for they're on the sort of the depleted side of mid-ocean ridge basalts. The dikes were basically the same composition, but just coarser grained. Site 1441, again, wasn't very successful. The bottom line is we sort of drilled into a talus pile, and the talus kept falling into the hole, and so we couldn't get very deep. However, it did drill a highly depleted basalt that is probably the most depleted basalt that's been basically drilled in ocean basins. And this its composition is shown here, and it's basically like the other phoric basalts, largely apheric, but it did have some clinopyroxene phenocrysts in it. Okay, so the bonanite holes, both of the holes were capped by what we called high silica bonanites. And these are the bonanites like you find on Chichijima. These are andesites, 59% silica. We have some that are up over 60% silica. Very high magnesium concentrations, but very low calcium and titanium. Again, these are very unusual lavas requiring shallow melting, highly depleted mantle, and lots of water. This shows one of our glassy samples. These are basically just orthopyroxene phenocrysts and glass, and the other crystals that you find in these lavas is olivine. Okay, those were underlain by what are we called low silica bonanites. They have less extreme compositions, still bonanitic, still high magnesium andesites. And their phenocryst compositions were basically, they included not only orthopyroxene and olivine, but also clinopyroxene. Okay, those are underlain by these evolved low silica bonanites. We call them high magnesium andesites. Basically, they're just low silica bonanites that were highly differentiated. And this is a picture, this is a plain polar light view of a thin section of one of these high magnesium andesites, just showing that it's mainly glass. And that's one thing that was really great about this expedition is we drilled a lot of glass, which gave us really pristine representations of the lavas that were erupting then. One other unusual lava type that we found in the drill hole was in site 1439, and these were basaltic bonanites. They basically had bonanitic titanium concentrations, and I'll show you incompatible element concentrations were basically bonanitic as well. But the other major element compositions were more like basalt. And then at the very bottom of the sequence were these coarser grained rocks that looked like the low silica bonanites, and we think that they are the feeder system for the low silica bonanites, and it could be that there actually are no phoric basalts in this hole, or in this area. We wish we could have gotten deep enough to prove that, but right now we're basically going with that the bonanites make up the crust in that area. Probably the most exciting post-cruise results so far were done by Daniel Heaton and Coppers at Oregon State University. And what they found with their very first age dates is that the age dates for the phoric basalts and the lower sections of the bonanites here are about the same. 51.88 million years here, plus or minus 0.55, and 51.84, plus or minus 0.22. So basically, the bottom line is the transition from basalt to bonanite only took no more than a few 100,000 years. And so these holes are about 15 kilometers apart. which would mean that if it was like 100,000 years between them, that would mean about a 15 centimeter per year sort of spreading rate. So at the high end of what we find in mid-ocean ridges, but we need to have more tight age constraints to really prove that. Okay, so this is what the trace element compositions of some of the glasses. So this is the phoric basalts. I have put some representative glasses here. Basically, these are all the incompatible trace elements down here. They're normalized to primitive mantle composition, plotted on a log scale. And the rare earths are basically shown in blue here. And then in red here are elements that are typically mobilized in subduction systems to produce arc magmas. And we can see for all of our phoric basalts, they have a light earth depleted pattern, and they don't have hardly any of these elements, or actually they have no enrichments of these elements from the subducting slab, showing that subducting slab actually did not contribute to magmagenesis during phoric basalt production. And just these lavas are actually quite depleted with respect to most morb. Here's a very depleted morb from the Indian Ridge, showing that ours are comparable to those, but we're even more depleted in the highly incompatible elements. These are bonanites. Here's a phoric basalt as a representation. Here's the low silica bonanite, showing that it's also like basically flat pattern rare earths, lower rare earth concentrations, but high concentrations of these fluid mobile elements. High silica bonanites have basically U-shaped rare earth patterns, extremely low middle rare earth concentrations, and very high concentrations of these fluid mobile elements. Another thing, though, is that these high silica bonanites are enriched in light rare earths. They're also enriched in zirconium. And I'll show on Wednesday some isotopic evidence suggesting that actually zirconium and the light rare earths are being transferred from the subducting slab, which means the subducting slab had to be melting. So basically, in this system, all of these elements, with the possible exception of niobium, have been mobilized from the subducting slab. Okay, so one last trace element plot. So this is two highly incompatible trace elements, barium and rubidium, over zirconium. Because they're divided by that have the same denominator, any straight line in this plot is mixing. So bottom line, and actually I've also shown mid-ocean ridge basalt compositions from Jenner and O'Neill. So bottom line is phoric basalts basically have compositions that are like the depleted end of mid-ocean ridge basalts, same sources, same kind of melting processes. Low silica bonanites basically look like they're mixtures of something that had composition about here with phoric basalts. And what we think was going on is basically two sources were generating magmas at the time. There was the phoric basalt source, and then the low silica bonanite source was when the subducting material started becoming involved in magmagenesis. And then the high silica bonanites look like they're mixtures of something more like out here with sort of an average low silica bonanite. So it means that basically you have this sequence of sources that that continue to appear in this subduction initiation sequence, and because these, the high silica bonanite falls here, the subducted material composition must have been quite different than the low silica bonanite material. And also, the last thing about this is that these lavas right here are the last ones out. This is the topmost lava at site 1439. So what we think basically happened here, okay, I'll be real quick, that these basically two sources were occurring at the same time. Basically, low silica bonanites, though, later were flushed out by the high silica bonanites entering the system. So I guess I'll have to skip that one. So bottom line, this is what we think happened there. Basically, we had the subduction start, produced phoric basalt genesis by C4 spreading. A new source appeared later on, producing the low silica basalts, and this only happened within a very short period of time. And then later on, the low silica bonanites were basically flushed out of the system by volcanism related to the high silica basalts, or excuse me, high silica bonanites. And I need to end, so thank you.
Thank you, Mr. Mark.
The next talk is on IODP deep riser stratigraphic drilling in the Southwest Pacific, tectonics, climate, and ancient life on the Lord Howe Rise, continental ribbon. And the talk will be given by Ron Hackney.
Thank you very much. It's great to have the chance to be invited to come give you an overview of this main drilling on the Lord Howe Rise. For many of you may be thinking about, okay, what's the Lord Howe Rise? There is that, what is that? If I maybe quickly turn that over to Northern Zealandia, that's maybe a bit more common in people's minds at the moment, looking at the new attention this new continent has had. So Northern Zealandia, or Zealandia itself, you see here a picture of this submerged continent, of which only 5% is exposed above the ocean. So Zealandia sits here and it's supposedly the 7th largest continent. According to Nick Watermer at New Zealand and his colleagues, meets all the criteria of being a continent. It's elevated relative to oceanic crust. Its crust is thicker than the oceanic crust and has seismic velocities that are continental. Has delicious continental rocks, and it's large enough to have well-defined geological limits.
Is that better?
Sorry. So Zealandia is there as a continent. What's the Lord Howe Rise? Well, we could suggest that the Lord Howe Rise is really the backbone to Northern Zealandia. So it's this elevated plateau that comes down along the axis of Northern Zealandia here. It's about 1,600 kilometres long, 400 or 500 kilometres wide, and it's made up of a series of basins and ridges in water depths up to about between about 1,000 and 4,000 metres. So there's a profile here extending from the eastern Australian coastline across past New Caledonia. So you can see oceanic crust in the Tasman Basin, the extended continental crust of the Lord Howe Rise itself, coming through the New Caledonia Basin onto the Norfolk Ridge, which is extending down there from New Caledonia. So what's special about Zealandia? You could argue that this part of the world is one of the last remaining frontiers in geoscience. Northern Zealandia represents one of these extended continental ribbons. There's a picture here showing that it was adjacent for a very long time through the Mesozoic to a subduction zone at the eastern margin of Gondwana. And this little pink bit that's sort of in here is the future Lord Howe Rise, and it's separated from Australia during the Cretaceous, roughly 80 to 50 million years ago. So the rift basins on the Lord Howe Rise now record 100 million years or more of tectonic and climate history in this region at the eastern edge of Gondwana. So what about these continental ribbons? They're pretty significant in, I guess, plate tectonics. They're long, narrow ribbons of continental crust. They form in possibly a number of ways. One way is as migrating arcs above retreating subduction zones, and that's captured in this image to the right here. So in the lower image, you see here subduction at a continental margin. Eventually that slab will then start to roll backwards, roll oceanwards, so trench migration, oceanward trench migration. And you can sliver off a piece of the continent and end up with an isolated piece of continent here, a ribbon, and extension in between next to the continent. So in the case of the Lord Howe Rise region, we would have the Tasman Sea Basin in here, Australia off to the left, the continent, and that continental ribbon sitting next to it, with possibly with the old subduction zone there. So the ultimate fate of these continental ribbons, they'll often collide with other continents as accreted terrains, and it's one mechanism we can still, they become, I guess, the building blocks of continents. So I don't have time to go into it today, but it could be that these continental ribbons are a key to understanding the driving forces of plate tectonics. So whether it's a mantle-driven process or a self-organised process driven by subduction. But you can quiz me on that later if you like. So the Southwest Pacific, where the Lord Howe Rise sits, is actually a bit of a data gap in terms of paleoclimate through to the Cretaceous. So in the Southwest Pacific, these constraints are quite limited. Some of the questions that are key in this region are what's the southern hemisphere extent of these ocean anoxic events, these organic rich rocks which are related to significant climatic events, mass extinctions, climate warming. And you can see a picture here showing the distribution of ocean anoxic events. In the northern hemisphere there's a concentration, southern hemisphere there's not so many, but we're also lacking the data there. So this little corner of the Southwest Pacific is probably a key location if we want to try and constrain some of those paleoclimate considerations in the Cretaceous. If we get cores from the Lord Howe Rise, Northern Zealandia there, then that'll help us come up with this high-resolution archive of Cretaceous climate variability in a region where we don't have much data. And there's a plot here of predicted sea surface temperatures for various levels of various concentrations of carbon dioxide in the atmosphere. And in the southern latitudes, there's not much data, and some of that data is quite scattered, making it quite difficult to constrain some of these models. So by drilling in this part of the world, we've got an opportunity to fill some of those data gaps. We heard a little bit earlier in the first session about the limits to life on Earth. These limits are still to be determined. There's I guess the famous example now of the microbial communities 2 kilometres deep in 20 million-year-old coal beds off in the forearc of Japan. And again, any opportunity to test what the limits of life are. If we're going here to the northern Zealandia, we've got a thick continuous Cretaceous sequence representing a time period of 100 million years. That's a unique opportunity to really test and push those limits of what sort of conditions and climates and paleogeography can still support life. So what do we know about this region? Okay, I've tried to make the case there for why it would be important to go there. What do we already know? The current understanding of this region is based on really a collection of 2D seismic reflection data. You can see a map here on the right. The yellow line outlines northern Zealandia. The white lines are all the seismic lines here. There's kind of an orange line through here, which was a recent Geoscience Australia JAMSTEC survey to constrain some of the crustal structure there as part of site surveys for planned IODP drilling. That's the red dots here. There's obviously gravity and magnetic data, some ship track data, satellite-based data, correlations with onshore areas from the few places where we can actually map the geology in Zealandia, and very limited number of dredge samples. These triangles here represent dredge samples, which are for samples of the Cretaceous and older for that time period we'd be interested in. And there's been some ocean drilling. You can see the coloured dots here. The yellow ones are the DSDP holes from quite a long time ago now, but the deepest of those reaches only about 500 metres below the seafloor to the very latest Cretaceous. And the real issue here when we want to know something about Zealandia is our knowledge is limited by a lack of rock samples. So we don't have those rock samples. So how do we go about that? Well, accessing the rock samples, I mentioned the drilling, but so far it's not very deep. From dredge samples, but there's a lot of post-rift cover in this region which prevents us getting access to these deep rift basins. So I'll show you a seismic section here again. This is that long profile across the whole region. We're looking roughly in this area here. So you can see rift grabens here up to about 5 or 6 kilometres deep, intervening horse blocks. But on top of all of that, there's this 500 metre thick, roughly, post-rift pelagic ooze that's covering over everything. And the vast majority of the Lord Howe Rise is covered by this stuff, meaning it's very hard to dredge any samples. So obviously the next best thing is maybe to try and drill into one of these basins to get the samples. So to that end, we've put together, myself and a large number of colleagues from dominantly Australia and Japan, but from around the world, this proposal, which is the Gondwana margin deep drilling. It's split into these 3 themes, which unsurprisingly relate to that case I tried to build up for you for why we would go and drill here. So in the Earth theme, defining the role and importance of these continental ribbons in plate tectonic cycles, rifting and continental evolution, oceans and climate, to recover this new high latitude data to better constrain the timing and nature of the Cretaceous paleoclimate and excuse me, the link changes in ocean biogeochemistry. In the life theme, again, to test these fundamental limits of life on Earth. So the plan in this proposal is what's shown in the map here on the right is the sediment thickness here. So some of these sedimentary basins in this region on the Lord Howe Rise reach 5 or 6 kilometres depth. The red dots represent the riser sites that are under consideration. There's a number of them, but we'll ultimately only drill one deep riser site. And the idea there is to recover a complete Cretaceous section through one of the rift basins into the pre-rift sediments and hopefully into the basement as well. We're looking at drilling probably roughly 2.5 kilometres below the seafloor. And I said here, we're aiming for 100% coring of this Cretaceous strata so we can get that full geological and paleoclimate story. There's also a plan to drill a couple of riserless shallow holes into basement horse blocks. That's these yellow dots here. And they're much shallower, but they're really just targeted to try and get to this basement and characterise the basement to the Lord Howe Rise. I'll just in the next slide, have a closer look in here to some of these sites. And the background here is now the water depth. We're looking at water depths of around about 1,500 metres. And what's shown here is, again, these sites here. The dashed lines are existing seismic lines. The black lines are the site seismic lines that were collected as part of the GA JAMSTEC survey in April, May last year. And I'm just going to show you a couple of examples of the seismic lines to show you what we're looking at drilling here. The interesting part about that was when we originally put in the proposal, we were focused on this area. As is often the case when you collect new data, the ideas and the picture of the area changes, and we're now looking at more likely drilling up in this northern part up here. So I'm going to show you a couple of seismic lines coming roughly through here, and one of the lines up here, just to give you an impression. So in the top section there, this is the preferred site prior to the survey, and below is the currently preferred site. So what you're looking at in these seismic sections is obviously the water is up here. So we're roughly 1,500 metres of water. The basement down here is looking reasonably bland. In here there's some uncertainty whether we are at the basement or not, or whether there's some more sediment deeper down. We're looking here at the Sin Rift sequence. So this is the Cretaceous sediments that are related to the rifting, the separation of Northern Zealandia from the rest of Gondwana. So this is our target interval in through here. The post-rift sequence is above it there. We're not so interested in that. That's much younger. It's not telling us that rifting story. And interestingly, in this other profile, there appears to be a whole lot more, quite strong reflectivity down below what's previously been picked as the bottom of the rift sequence. So this was not well imaged in the previous surveys. So this site becomes the sort of the preferred site because we're far more confident that we're going to get all of the geology that tells us that full geological history of the separation of Northern Zealandia from Gondwana. So that's just a final point here, this related to this uncertainty of what's in the basement. There is a very strong sill there. We're not sure how that's influencing the reflectivity below. And there are some other considerations which suggest to us that maybe there's more sediments down here than we think. So just to quickly touch on it, I'm coming to the end now. I'll just show you an example of one of these shallow basement holes. So we're looking here, much shallower water depth, and a couple of seismic lines crossing over that site. And really we're looking into a basement horse block here. You can see the basins on either side, not so well imaged on this side, but also it's present here. So really just drilling through these post-rift sediments and it's finding out what's in the basement. And this bland basement here with not much reflectivity may represent the metamorphics and granites of a Gondwana margin magmatic belt related to that long-lived subduction there. So it would be quite a key thing to try and find that. So just in summary, the Lord Howe Rise is a keystone in the Cretaceous global tectonic and climate puzzle. I've hopefully built up the case for you suggesting why we would want to go and do deep stratigraphic drilling here, because it'll provide the rocks that record that Southwest Pacific Cretaceous tectonics and climate, and a new environment in which to test the limits of life. So this Gondwana margin deep drilling proposal, it's a multidisciplinary, internationally significant project. It addresses many of the challenges I outlined in the IODP science plan. Recently, earlier this year, the proposal was approved by the Science Evaluation Panel and also the CHIKU IODP board. And we're currently working very closely with CDEX and others in JAMSTEC to plan for this drilling. And at the moment, it's scheduled for the second half of 2020. And one of the biggest focuses, especially for us in Australia, is to start making this case to government. Now that we know we've got a fully backed proposal, we can make that formal bid to the Australian government for the funding to support this initiative. So that's a summary of what I wanted to tell you about. There's obviously a big team of people involved here. These are the proponents here, but there's also a whole team of people at JAMSTEC and others around the world who are working on some of the site survey data, and I would encourage you to come along to a presentation tomorrow afternoon by Brian Boston, and also a poster by Flora Gallet, who will telling us something about some of the results from this site survey that we conducted in the middle of last year. So thanks for your attention.
Our next talk is to be given by Katsuyoshi Michibayashi on mantle drilling projects, M2M, 4ARC M2M, and ICDP, Oman DP.
Okay, before my presentation, today we have a JDESC town hall meeting. Please join us at 6:30. And poster session is here. Please turn left, then find out our central cafeteria. Okay, please. So, mantle drilling project. Today, this talk is I just put only my name because this is personal point of view, rather. So anyway, M2M is not just one enormous project. We have some other projects. So I'd like to briefly introduce you what is going on about mantle drilling project. Okay. So maybe scientific ocean drilling, it initiated around 1950s, but maybe we may put in the further in the back to discovery of Mohorovičić discontinuity. This may be the really start. So firstly, I'd like to a little bit explain about this discontinuity. Mohorovičić discontinuity, we call MOHO, is an intense seismic reflection, which seismically defined the boundary between crust and mantle in the Earth. So this is in the ocean case, is always around between 6 and 7 kilometers. And this MOHO, we can find it all around the world. And then from the ocean to the continent. And in contrast to the continental MOHO, this is the color is going to, the reddish color become much more thick MOHO. That means the thick crustal thickness. In contrast to the continent, ocean side is very much bluish. That means quite similar thickness. So this is very important for the Earth history because constant MOHO depth in the global ocean is the evidence for homogeneous cooling of the Earth. However, last 50 years of ocean floor science, we now know crustal section we revealed is not just homogeneous. It's quite different from the one ocean to the other. So this is actually compiled by Henry of my next talk. This Pacific Ocean this is a kind of typical crustal section we really know. So MOHO is the crustal boundary between crust and the mantle. However, if we go to the Atlantic Ocean or Indian Ocean, this kind of picture is quite different. However, MOHO is almost same depth, same constant. Why? So, although the MOHO interface model has this kind of variation, why the MOHO depth is so constant is unsolved. Then, this MOHO project has been initiated in the back to 1960s. This project is actually in the 1960s here, done by the United States. Mostly Walter Munk proposed this MOHO project. And he is still alive in the age of 98. I met him in the last 2 years ago when I attended the SEP meeting. Right? And so he is so pleased to find out the current situation of the mantle project anyway. Okay? Then this project is actually making, what is it here? A maximum penetration is 183 meters, and then 14 meters of basalt. And then this is actually a very beautiful story published by John Steinbeck. However, this project is terminated in 1966. But although a MOHO project has been terminated, after that we started a deep sea drilling project, then going to the ocean drilling project, ODP. Then this is first integrated ocean drilling program, IODP. Then after that, 2005, we got the CHIKU. So for CHIKU, since we have a CHIKU, we got a new MOHO project. That the MOHO project has been updated to be MOHO-2 mantle, M2M, now we're calling M2 in 2012. So this is a new ocean drilling proposal for IODP, submitted in April, and the 7 lead proponents, including myself, dominated by Japanese proponents. This is a picture of the new M2M project. So we will find somewhere between Japan and North America some plate, then going to the 6-kilometer drilling through the crust, then try to reach it to MOHO. So at the moment, three candidate sites were selected. Then, however, additional site survey are required. Then here, I'm very pleased to tell you, site survey began in this year for this Hawaiian site. So it starts with the site survey now, although still a long way. Yes, yes, it's coming later. But it is a still long, long way to make it happen. So, toward M2M, we would like to use Chikyu along the way. So, first one, Chikyu meets ICDP Oman drilling project in this summer. So, this is the Oman drilling project. Is the lead proponent is Peter Kellerman, the Yorg Matter, and Damon Teagle. And then project steering committee, including myself. This actually, yes, it's then so background of the Oman drilling project. This is the mountain of the Oman, and it's located in the eastern side of the Arabian Peninsula. If you go almost everywhere, you can find this kind of mountains. Can you see this little bit darker? Color is different here. This one, this in most of case, in the top is the ocean crust. Yeah, in fact, it is gabbro. Then here is the Danite, then Hartbergite. This is actually expected by cluster section, a proposed cluster section for Pacific plate. So Oman ferrite is a kind of analog geology for ocean floor. So this here could be the moho in earlier time, not now. Then the Oman is here, and so this project is going to sample the whole of ferrite sequence from crust to mantle by core. We get a continuous core, but no way to core everything from top to the bottom. So now we decided that in the southern part of Oman ferrite, there's this point. Then each hole we make is 400 meters in most. So then at the key section like this. So after connecting this, comparing these cores, then we somehow get more information and a new knowledge on the cluster section. Okay. Then Chikyu meet Oman drilling project. What this means is that we are going to describe Oman drilling project core in Chikyu, while Chikyu is import from 15th of July to 15th of September, 2 months we do. How we do it? Chikyu is not just a drilling vessel. They have a wonderful laboratory area. So we thought maybe we can use this laboratory for the core. So now we are shipping the Oman core from Oman to Japan. Now first core already arrived in the last month. Then second core, 800 meter core, will be arrived next month. So this is the first one. So another project is we are going to take Chikyu. Well, I'd like to take Chikyu to Bonin Trench. So this is the IBM project. Just Mark Regan presented the recent result of Expedition 352 in here. So Mark's presentation about here, we drilled using a JOIDES resolution to drill in this volcanic sequence in here. Then on this Bonin Trench, if we go to the deeper side, we can find gabbro and peridotite. So this is the idea of the four-arc mantle. So this is Expedition 352. We're using Chikyu to go into the deep drilling to the crust and the mantle in the much more deeper ocean floors. This we call four-arc M2M project towards the deepest ocean. Four-arc M2M will drill into mantle from seafloor at 6,000 meters below sea level instead of 6,000 meters of oceanic crust. So technically it should be easier. So we hope to submit a full proposal of four-arc M2M in a few years, we hope. But this is hoping. We need a many site survey, things. Anyway, I'm hoping. So Chikyu will drill into the lower crust and mantle at 6,500 meters below sea level, and then a four-arc M2M geological survey begin in this summer. So we are going to using Shinkai 600-500 to make 3 dives to see if we can find any peridotite rocks or not. Here is the site. Yes. So Chichijima is here, and this is expression 352, just Mark presented. So now we know, we get the peritotite from here and here. So, and in this summer, we are going to use Shinkai 6500 to this and this two area to make sure if we really find out peritotite again. So, mantle drilling projects have three. M2M site survey for the Hawaiian site begin in this summer. ICDP Oman drilling project is going to use CQ for its core description in this summer. HOAC M2M geological survey begin also in this summer. Then one more thing. A new proposal will be submitted in the next year, we hope. That is the Godzilla Megamillion project. It's coming soon. Godzilla Megamillion is located quite far from Japan. So we are going to make a proposal in 4 weeks proposal. And we have already 3D seismic profile. We have a geological survey. We have an international workshop too. So its condition is already ready. So we should submit full proposal. So this is the most closest project we think. So maybe the first mantle drilling project before HOAC M2M and M2M. Thank you very much.
So we shall move on to the last talk of this morning session, Project Slow-Mo, drilling through the lower crust to Moho at the Southwest Indian Ridge. And Henry Dick will give the talk.
Okay. Project Slow-Mo, the best thing I've done so far is dream up the acronym, is to determine the nature of the intrusive crust in Moho at a slow-spreading ridge. And this project has complements greatly. Let's see if I figure out how this works. Oh, there we go. This project is not in competition with drilling in the Pacific Moho. And the reason why is shown here by these two cartoons. This is the geology of a slow and ultra-slow spreading ridge as we now understand it. And in this particular case, we're forming a core complex. The deformation that is associated with lithospheric overturn extends all the way up to the base of the sheeted dikes. And what you have in here is dynamic accretion, where you have small intrusions coming in, and you have building things up from below, and also being rafted upward by the motions here. And you have an extremely complex stratigraphy of small intrusions, dynamic deformation going on while intrusion is occurring, and you have a host of processes here that we've really never viewed before in the ocean ridge. We know this from studies of the earlier cores taken here, studies of cores at the Atlantis Massif site. You look at the fast-spraying ridge, and most notably, it's passive accretion. You have a main crystal mush zone, and then meltlands at the bottom and meltlands at the top, and you're passively accreting the ocean crust. You get a dramatically different stratigraphy. Lithospheric overturn happens at the base of the crust, so you don't get that up in the crust. The other dramatic difference, which we believe is the case, is the Moho in the Pacific, we believe, is the crust mantle boundary, as originally hypothesized by Sir Harold Jeffreys. However, here, we believe the Moho is likely to be a hydration front. And this leaves us with some really interesting possibilities that I'll discuss later for what is occurring down here. Now, our goal is to start at the top of this section and to drill down all the way to 500 meters below the Moho. And on the way, we believe we'll penetrate the crust mantle boundary. The project is supposed to occur in two major phases. Phase one has already started with leg one in December and January of 2015 and 2016. There should be a second leg to continue that. And the objective here is to drill down through the crust mantle boundary in those two in the first phase. And then to come back with a CHICU for phase two to continue on down to 500 meters below MOHO. So these two sections are the starting point for understanding the oceanic MOHO. And this is really a critical thing to understanding our planet. Now, the site that we're working on is here at Atlantis Bank in the Indian Ocean, about a 3-day stream south of Port Louis, Mauritius. And I'm reporting today on the results of the first drilling leg. Some of the objectives of this program are shown here. To drill to 500 meters below MOHO, of course, but to recover the full stratigraphy of the lower crust and to determine if MOHO is a serpentization front at a slow-spraying ridge. Discover if there's an entirely new planetary biosphere beneath the crust. Now, why would that be? Serpentization is a methanogenic process, and it provides food for biomass. And therefore, there is a really real potential that we have a major new planetary biosphere beneath the ocean crust, at least the slow-spraying ridges. That same process of serpentization potentially could do massive carbon sequestration, and so therefore we may have a major unknown in the global carbon budget, that we may discover a new reservoir that will link into that. Specifically, leg one's objectives is to drill as deep a hole as possible, log it, and leave it as an open legacy hole for penetration of the crust mantle boundary. That is obviously was the first goal. Determine the lateral stratigraphy of the ocean crust at Atlantis Bank. That is actually very important because the two long gabbro sections we have, the 1,400-meter Atlantis Massif section from the Mid-Atlantic Ridge and the 1,500-meter section at Atlantis Bank from 735B, are tremendously different. This section has intercalations of mantle peridotite in it. It has different types of gabbros. These sections represent the variability is so great that these are proportions of different rock types as you go down the hole. But we do not know if we have lateral continuity here, and that's very important if you're trying to set up a seismic laboratory, because one of the objectives of slow-mo is to drill 2 holes spaced widely apart, one hole from which we can do hole-to-hole direct seismic measurements of properties of the lower crust and get a better image of the MOHO beneath it than we can possibly get by doing reflection or refraction on a very rough seafloor. And of course, assess the biomass and bacterial fungi in the lower crust, and finally, to drill through a full magnetic polarity interval. We've achieved the first 3 objectives. There's something to go on objective 4. The site is a 12-million-year-old oceanic core complex located about 100 kilometers south of the present-day Mid-Atlantic Ridge. And this is a wave-cut plateau that was once probably as much as 1,000 meters above sea level. And our prior drilling here is shown in 735B, and originally we felt that there's a series of stratigraphic units with upwardly differentiated crust. This is being modified. One of the major features was intense crystal plastic deformation that was found up and down the hole, often localizing melt intrusion. This is the old seismics from White and Minshall at University of Cambridge. And you can see where 735B is, and you can see their stratigraphy. But they have 2 interpretations. One is that the MOHO is the crust mantle boundary, and the other was that the MOHO is a serpentization front. And so this stratigraphy would be what was predicted here, and this stratigraphy is what would be predicted here, and yet there are other possibilities to be determined. Our operations initially went off quite flawlessly. We used a drill-in reentry cone. We went down and did a survey, looked at the flat top of the seamount. These are fossilized carbonate beaches, and you can see the little sea stacks coming out from underneath. And then we drilled in a drill and guide base and dropped the funnel down on top of it. And that went very smoothly. This was a new guide base. and we're really pleased because this looks like it's going to be the standard from now on. It enables hard rock drilling and reentry sites to be set really well. We did some considerable operational problems, however. We drilled 789.7 meters. We'd hoped to drill 1,300 meters. We got 63% core recovery overall, and that's because several brittle fault zones were encountered down to 469 meters. This led to some losing of drill cones in the core, and finally we managed to fish out things with this thing, which drilled megacore. This, I think, is the thickest core ever drilled from the ocean crust. We also had a medical evacuation. One of the technicians had an eye disease, and he had to be taken back to shore, so we had to break off and spend six days steaming up to Mauritius and back again, and having him lifted off of the JOIDES Resolution off of Mauritius. This contributed, obviously, to why we did not get as far as we hoped. The first objective, as I mentioned, which was drilling down to the through a major polarity interval, we didn't quite achieve. We tagged it. We thought the polarity interval would be sloping down at this angle. We just tagged it. We got we started to get a magnetic reversals in the last cores when we were doing demagnetization in the lower temperature magnetization. The igneous stratigraphy was very similar to 735B. It was dominated by olivine gabbro with some intervals of grain size layering. A lot of abundant iron titanium oxide gabbro, and we're making a lot out of this because its emplacement is quite peculiar. It's often found along major shear zones in the core. There's possibly several repeating igneous units, and superposed in all of this are late stage evolved oxide saturated melts migrating through the pore space of a crystal mush, which modifies and spreads out the stratigraphy all the way up. And everything is overprinted by dynamic recrystallization. The crystal plastic deformation was more intense than we saw at 735B. Was that the ding? Yeah. You can see this in these cores, all this intense crystal plastic deformation. Brittle deformation, of course, was a bit of a problem. It was intense up in the upper part because we were drilling through a major fault zone. And then we went back to drilling conditions that we see normally at 735B. We actually had open circulation of seawater down to about 450 meters. And we had active carbonate precipitation on the rocks down there. And this, of course, led to our disastrous drill bits. The biomass, we found significant evidence for biomass in these cores. This is Ginny Edgecombe and Chris McLeod. And we did a lot of sampling all the way down. And they found a variety of signals here, the fungi and lipids and other biomarkers. So they were quite pleased. Here is one thing that was really an interesting aspect is that we had enormous publicity. And it just kept going and going and going and going and going and going. And did I mention going? This was my favorite. Great to lead to the disappointment of the Sunday Express, we did not cause a major earthquake and huge, massive tsunami. But we did get the ultimate in publicity, according to my kids. It doesn't come out. I'm sorry, Jimmy Fallon ended his show one day with a joke about our drilling. We made the Jimmy Fallon show, and that really impressed my teenage kids. He said that there's a bunch of scientists who are trying to drill through the Earth's core, and they weren't sure that this might cause a great disaster, but it'd be all worthwhile if it had a cherry core. So one of the things that was very clear is that the onus that was created in Project Mohole with over-budgeting and other problems has left the minds of the public, and they're extremely enthusiastic about these projects, both M3M and this. Because I've never experienced something like this. I spent 20% of my time dealing with the press on the drill ship. And we had a considerable outreach program, highly successful. The number of radio, TV shows, and recently after the cruise, there have been radio documentaries on the BBC about this. So I want to thank you for your attention. And I want to say that the original MOHO project was started by the US, but it's clear to me that it's going to be finished by the international community. And that is a wonderful thing. Thank you.